Okay, I want to start this lesson by pointing out that I've already posted the unit plan for this unit, Unit 3, on the website. And when you're finished the video, my assumption is that you're going to be ready to do the homework for day one. The second thing I want to point out is that I've also posted a link to a Khan Academy video, which relates very closely to some of what I'm doing today. And I think once you finish going through this video, it might be a good idea for you to look at his video as well, just to reinforce what I went through here. All right, so we're going to be looking today at the second derivative of function, so higher order derivatives. We've looked at first derivatives and we understand what they mean, we understand what they do, but what about a second derivative? What's the point of that? We're going to understand the meaning of both first and second in connection with the position function. We've done first derivatives on position functions, and we know they tend to tell us a little bit about velocity. Well, what does second derivative do? And we're going to be able to apply it to various problems. So that's the goal of what we're doing today. Higher order derivatives. Well, first of all, let's just use some notation here. The derivative of f of x, as you know, is denoted by this f prime x. If you want to get a second derivative, you just simply take the derivative of the derivative. So we're talking about f double prime of x, and it's referred to as a second derivative. In the Leibniz notation, if we start off with y equals f of x, we know the first derivative is written as dy dx. Well, the second derivative is referred to as d2y dx squared, as you can see what I'm pointing to here on the screen. Let's take our first question. Let's calculate the first and second derivative of the following. Typical polynomial, minus x cubed plus 2x squared plus 9x. So we know that the first derivative would be minus 3x squared plus 4x plus 9. And then the second derivative would just simply be minus 6x plus 4. So there you go. As easy as that. Of course, some of the questions will be a little bit more challenging. What if you had to do this, for instance, for a rational function? So here's a rational function. And our first derivative, of course, I think using the quotient law makes the most sense, would be to take the derivative of the top, which is 1, multiplied by the underived denominator, as you can see here, minus the derivative of the bottom multiplied by the underived numerator. So we'll have something looking like this. We've done a lot of these before, so none of this is going to be new to you. And then the derivative can be simplified to give you just simply minus 3 over 2 minus 3 squared. Now, if we're going to know another derivative, I'm thinking that it might make more sense for us to write it this way, and then we could probably use the chain rule. So using the chain rule, here's my second derivative. So my d2y, remember Leibniz notation, d2y over dx squared will be equal to 6 2x minus 3 to the power of minus 3 multiplied by the inner function, which of course would just be 2. And with a little bit of tidying up, it would look something like this. All right, so there's our first and second derivative on a rational function. So why do we need this second derivative? Well, I want you to think about when we use the first derivative of the position function and we got the velocity function. If we take the second derivative, which is the derivative of the velocity function, then we're going to get the acceleration function. So as it says here, if we have a function which represents the distance of the object from some start position, the s prime of t is velocity and s double prime of t is the acceleration of the object. So let me describe a few scenarios to you to hopefully make this more clear about the relationship between these three things. Let me start by saying that we have a position function. I'm not giving an actual function. I'm just telling you what the result of putting a value into that function is, and we're going to compare the three things and try to interpret them. So if I put 2 into this position function, my s of 2 is 4 centimeters. Think of 4 centimeters for the purposes of this little analogy or this scenario as being 4 centimeters above the starting point. If it was negative, it would be below the starting point. Now, the first derivative of that position function, of course, is our velocity. And in this case, it's telling us that putting 2 into that velocity function, that first derivative function, means that I'm moving at a rate or at a velocity of 2 centimeters per second. So every second, I'm moving my position 2 centimeters. The s double prime of 2 at the same 2 seconds says that even though my velocity is 2 centimeters per second, that is changing at the rate of 1 centimeter per second per second. Notice it says 1 centimeter per second squared. So I am moving at a particular rate, but that rate is changing. Think of yourself going along on the 401 and looking at the speedometer. So that tells you your velocity. But then you notice that the speedometer is climbing as you go along. So that means that you're accelerating, you're moving faster. That's what is happening here. So to summarize, I'm above the start. Remember I said that positive means that I'm above. I'm moving upward and I'm also speeding up. Compare that to this scenario. Some other position function gives me these values. S of 2 now says I am minus 4 centimeters. That would suggest I'm not above anymore, like in the first scenario. I'm now below. But S prime of 2, which is my first derivative, my velocity function, says that I am 9 centimeters per second. This is my velocity, which means that I'm changing my position at the rate of 9 centimeters per second. But furthermore, I'm moving upward. Even though I'm below, which is what the minus 4 says, I'm actually moving upward at a rate of 9 centimeters per second. But look at my second derivative. My second derivative at the same 2 seconds says minus 2 centimeters per second, which is saying that my 9 centimeter per second velocity is dropping at the rate of 2 centimeters per second. This means I'm slowing down. So I'm below the start, it's negative. I'm moving upward, positive. I'm slowing down, negative. Now, here's an important point to pay attention to. When these two things are positive or the same sign, I'm speeding up. When these two things are opposite signs, I'm slowing down. It's as if they're working against each other. One says I want to move up. The other one says I'm going to limit the amount that you're moving up by per second, which means I'm slowing down. How does that compare to this? Different position function. I'm now putting 2 seconds into this and getting an 8 centimeter result. That again means I am above the start, like in A here. I'm above the start. The velocity function is giving me a minus 4 centimeters per second. So that would be equivalent to me moving downward this time. But look at my second derivative. My second derivative says that I'm moving downward, but I am okay, look at this. It's a positive, which means that even though I'm going in a negative direction, I'm adding 2 to that, which means that I'm slowing down this downward direction. That's how you need to look at this. So this is actually slowing down as well. So I'm above the start, I'm moving downward, but I'm slowing down. Again, notice that these two things are opposite signs, and that's the key to understanding when you're speeding up or slowing down. Opposite signs means they're almost working against each other. The same sign means they're working together, which makes that you're speeding up. Okay, look at the last one. Position minus 900. So I'm below the start. My S2, which is my velocity, is minus 10. So I'm moving downward. But this S double prime of 2 is also negative. So it means that I'm getting even more negative. And that actually means that I'm speeding up. I'm speeding up as I'm going down. I'm negative here, and this is making me become even more negative. So I'm actually speeding up in a negative direction. So I'm below the start, moving downward, and I'm speeding up. So look out for the signs of these two things, velocity and acceleration. If they're the same, as in the case of A and D, I am speeding up. If they're different, as in the case of B and C, then it means I'm slowing down. Problem C. Object is moving along a line, etc., etc., and I give you the actual function this time, and I'm asking you for the P of t, which is a position of the object at a particular time. So here's the question. What's the object's position at 3 seconds? Well, that's just putting 3 into the function. So here we go. P of 3, 36 centimeters. I'm going to say it's on the right. Now, I've been using above and below, but let's also use right and left. If it's positive, it's on the right. If it's negative, it's on the left. If you look at the Khan Academy video, I believe he uses left and right as well. So we tend to use both conventions. What about the velocity at that particular time? Now remember, velocity is the rate of change in distance over time. So now I'm going to need that first derivative, so p prime t, and that's of course 10t minus t squared. If I put my 3 into that, that gives me a value of 21 centimeters per second. That's my velocity at the 3-second mark. So I'm 36 centimeters on the right, and I'm moving right at a velocity of 21 centimeters per second. What about my acceleration? Now that's how my velocity is changing. And at the same 3-second mark, I'm going to need my second derivative, which is 10 minus 2t. And that works out to 4 centimeters per second per second. Again, per second squared. I'm speeding up to the right. Again, positive velocity, positive acceleration. It does mean I'm speeding up to the right. They're both in the same direction. Now, I kind of want to sort of make that a little bit more clear by looking at some graphs and then seeing if we can, using the graphs, answer the question that we just asked from the previous slide all over again. These are graphs that are for the position, the red line, for the velocity, the blue line, and for acceleration, the green line. I want you to notice that the velocity is really just a parabola. It turned out to be a quadratic. So when is the object moving forward? The object is moving forward as long as my velocity graph is positive. We talked about positive before, meaning you're moving in a particular direction. So looking at this particular graph, if you can, and if you look at the function before, you notice that it's 10t minus t squared. That's, so if we factor it, we'll have the two zeros there, 0 and 10. And if we are asking where the graph is positive, it's between 0 and 10, right? You can see that the graph is, opens down, and between 0 and 10 is positive. So if you just want to know when it's moving forward, we're not talking about when it's speeding up or anything, just when is it moving forward. Even though it seems like it's going up and coming down, going down doesn't mean that it's not moving forward. It does mean that it is not accelerating. Sorry, it's slowing down or decelerating. But being above the x-axis just means it's moving forward, period. All right. The next thing we want to look at is when it's speeding up. And that's the thing that I know we want to make sure we're completely understood on. So I want you to look at where we talked about the interaction between acceleration and velocity before. So I want you to look at where the acceleration is positive, and that's of course anywhere from 0 up to 5. It's positive anywhere between those two. All right, you can look at the graph and you can see that it is negative for a certain section as well, from 5 until infinity, but it is positive from 0 up to 5. Notice that I'm not looking at anything to the left of 0 because we're going to assume that the domain of the function is in fact 0. So when is it speeding up? Acceleration is positive, so that's between 0 and 5. It's speeding up because, between 0 and 5, because both the velocity function and the acceleration function are both positive for that region from here to here. But do you notice that after 5, this becomes negative? So even though this part is positive, this part down here is actually negative. When does it speed up again? Look to the right of this, to the part of the function where the velocity drops below the x-axis and means it's negative. And this has been negative for a while, so they're now both negative once you get past 10. So where's this speeding up? It's speeding up from 0 up to 5 if you're following where I have the mouse pointed, from 0 to 5, and that's because both graphs are in the positive above the x-axis. Once you get past 5, this one stays positive, this one drops to be negative. So it's actually slowing down here. Then when you get to 10, what's happening is that both become negative, so you're actually speeding up in the opposite direction, because this is negative and that's also negative. So that's one way that you can sort of, just looking at the graph, figure out what's going on. Another thing that you'll notice that some people use to figure out when it's speeding up or slowing down is just looking at the velocity function. When the velocity function is positive, but also when The slope is positive is when it's speeding up. So at this part of the graph here, it's positive, but it's also a positive slope. We need those two things together for it to be speeding up. If you go past 5 and you're going towards 10, you notice that although it's positive, the slope is negative, and therefore it's slowing down. Over here, it's negative, but the slope is also negative, and that means that you're speeding up again, but in the opposite direction. So hopefully that makes sense. So I hope that helps. Sometimes you can use number lines and look at where they have overlap for where it's positive, where it's negative. But I'm going to leave it on that note. Go get some homework done.